So this video in particular aims to be a somewhat of a consolidation of integral techniques, basic integration, and then we're going to look at fractional powers and just normal powers and how to take integrals of subtracting and adding functions, and then we'll look at U-substitution, and then we'll look at finding the original function given initial conditions, and we'll look at taking the integrals of quotients, and so on and so forth. And hopefully we can speed through this and sort of review, and we'll sort of break it down, but this is more so focused on the computational aspects of taking integrals rather than the conceptual aspects. The first point to essentially remember is that if you have an integral, or if you have this notation, it's sort of an elongated s, and you have dx. Whatever is in between is what you are taking the integral of. So if I have 2x in between, or if I have x squared in between, I'm essentially taking the integral of x squared. I'm finding the antiderivative of x squared. So x squared is my function, and once I solve this, I will get the antiderivative. So I'm just going to tell you that the antiderivative of x squared is x cubed over 3. And the basic idea here is that what you want to remember is that this is another function, right? This is another function. It's x cubed over 3. Now, we would essentially only say that this function is the antiderivative of this function if I can take the derivative of this function here, and I would get back the original function. So I know that was a lot, but if you bear with me here, if I take the derivative of this, what do I get? So the derivative of this is 1 over 3 times 3x squared. The 3's cancel out, and I have x squared. So you can actually see that if I take the derivative of this big F, this function that I'm calling big F, then I get back the original function, which means this is the antiderivative. Of course, we haven't covered actually how to get to this position of taking the antiderivative, but the basic rule is that if we're given f, then big F is the antiderivative of f if and only if big F prime gives us the original function. So another example, right? So if I'm taking the integral of, let's say f of x is equal to x cubed, right? And I'm asked to find the antiderivative. Well, I would put it in this elongated s notation, with my dx sort of sandwiching this function, and I would produce another function. And I'm just going to tell you for granted that the other function that I'm talking about is x to the 4 over 4. Now, this is the antiderivative of this function, and it meets the classification of being an antiderivative because if I take the derivative of this function, I get back the original function. You can actually see that in action. So if I take the derivative of this function, I'll have 1 over 4x I'll have 4x to the third. The 4's would cancel out, and I would get x to the third. So you can see that this is in fact the antiderivative, and you want to hold all your antiderivatives to the same level of scrutiny. You want to take the derivative of them and see if you got back the original function. But now the question is, how exactly did I arrive at the antiderivative? How do we calculate antiderivatives? And the basic idea here is the power rule. So this is the first rule of taking the integral, as they call it. Finding the integral is the same thing as finding the antiderivative. These are synonymous terms. So if I want to essentially take the integral of x to the n, right? Now, when I say n, it could be any number. It could be x squared, it could be x to the 4th, it could be x to the 5th. It really could be anything. But if I want to find the integral of a function that is of the form x to the n, then I would essentially be doing x to the n plus 1 over n plus 1. You can verbalize this as adding 1 to the exponent and dividing by that exponent. For example, if I had x to the third dx, then I'm going to add 1 to the exponent. This is x to the fourth, and I'm going to divide by that exponent, which is 4. And I would add a plus c, which is the constant of integration, and that would be my antiderivative. So another example, if I had my same elongated s and I had x to the fifth dx, I would essentially say I would add 1 to the top, I would add 1 to the exponent, this would be x to the sixth, and then I would divide by that exponent that I added at the top, which is 6. And then I would add my constant of integration. So for another example, if I had an elongated x, and then I had x to the seventh dx, I'm going to add 1 to the top, and then I'm going to divide by whatever I had added on the top. And I would add my constant of integration, and that takes care of that. Now, I've actually only covered the power rule, but what if we had something of the form, let's say 2x squared? What would we do in this case? Well, the rule that we want to remember is that if we're taking the integral of a constant multiplied by a function. Now, in this case, this is the constant. This is the constant. This is the function. So how exactly would I take the integral of this? Well, the trick is to pull the constant out. So you're pulling the constant out, and you're just taking the integral of the function. So just take the integral of this and then just multiply by whatever that constant was. So in a way, you just ignore the constants. So you can pull this integral, you can pull the constant out, and then you're just taking the integral of the inside function here, or of the function. And then we know that the integral of this is x to the third over 3. I added 1 to the top and divided by whatever I added. And then so my answer is 2x cubed over 3 plus c. So for another example here, if I had 4x to the third dx, I am essentially going to pull the constant out. Now, I actually don't have to pull it out. I could just ignore it, and it would still work. So I'm just going to ignore the constant. So it's just 4, and then I'm going to do the integral of x cubed, which is x to the fourth over 4, and I'm going to add my c, and that's it. So for another example, I'll have the integral of 8x cubed dx. So I'm going to ignore the constant. I'm going to add 1 to my exponent, which is 4. I'm going to divide by 4, and I'm going to add my constant of integration. I can simplify a bit. I can say that 4 goes into 8 twice. So I'll say that this is 2x fourth plus c, and that's my answer. Now, we've actually been able to cover the power rule and the constant multiplied by a function rule for antiderivatives. But how exactly do we do something like this? So suppose I had 2x to the fourth plus 3x squared minus 2x plus 3 dx. So you can see that the function that I'm taking the integral of is now quite large. And there are a couple things that we want to consider. The first is that if you're taking the antiderivative, of, let's say, two functions, f of x plus or minus g of x, it doesn't matter, then this is the same thing as just taking the antiderivative of f of x and then just adding or subtracting whatever you were doing by g of x. So what do I mean by that? I mean, if I had the antiderivative of 2x squared plus 4x squared dx, then essentially what I would do is I would just take the integral of this, and I would just take the integral of this, and then I would just combine them by addition. So I would say that the integral of this is, I'm going to ignore the constant, and then I'm going to add 1 to the top, x cubed, divide by whatever I added. And in this case here, I would ignore the constant again. I'd add 1 to the top, x to the second, and then I'll divide by whatever I added. Remember that there was an implicit 1 at the top. And then I'll add my constant of integration, and that's essentially my answer. So the same thing we essentially do here, where we take the integral of this, this, and this, and then we add them or subtract them together, whatever operation is bounding them. So I'm going to ignore the constants. I'm going to add 1 to the top, divide by whatever I added, ignore the constant, add 1 to the top, divide by whatever I added. And then here, ignore the constant, add 1 to the top, divide by whatever I added, plus 3x. So the rule here is that if you have a constant and you're taking the integral of that constant, then you just add an x at the end and you should be fine. Plus my constant of integration. So we'll look at another example. If we had So the basic idea here would essentially just be ignore the constant, add 1 to the top, divide by whatever I added, plus ignore the constant, add 1 to the top, divide by whatever I added, ignore the constant, add 1 to the top, divide by whatever I added, and then add 1 to the top, divide by whatever I added, minus 2. So that's just a constant. I'm just going to add an x at the end, and that is my antiderivative. So we've covered basically polynomial integrals. We've covered the power rule. We've covered the multiple rule. And now we're essentially looking a little bit into fractional powers. So what if we had something like this, x to the 2/3, right? What would we do? What would we essentially do in this case? Or yeah, I think actually, let me go ahead and simplify it here. What would we do in this case here? So the basic idea is that we don't violate any of the rules that we have established so far. So the integral for this would essentially be, so I'm gonna essentially add 1 to the top, which is x to the -2 plus 1, and I'm going to divide by whatever this was. So -2 plus 1 is -1, right? So it's -1. So the answer is x to the -1 over -1. Which is -1 over x. Why did I say that? Because if you have x to the -1, then this is 1 over x. If you have x to the -3, it doesn't matter what exponent you have at the top. If it's negative, then you can write it as a fraction. But when you write it as a fraction, you have to make it positive. Now you can think of this as simply, if you have a to the if you have x to the -4, and I want to take it. So this is actually x to the -4 over 1. If I want to take it down, I have to switch the sign of the exponent. So this would be 1 over x to the 4th. If I had 1 over x to the 4th, for instance, and I wanted to take it up, then I would have to switch the sign. I would have to make it negative. So that would just be x to the -4, and then I would call it a day. So that's essentially why I took it down. I still had that negative. I took it down, but I made that 1 positive. So I said it's -1 over x. So let's go ahead and do this problem here. So they're saying that f of x is equal to 2x cubed minus 2 over 3 x squared plus 5x. So what is the antiderivative? So if I wanted to find the antiderivative of this function, then I'm going to put it in this notation. And essentially, so I'm going to ignore the constant. I'm going to say this is 2. I'm going to add 1 to the top. And then I'm going to divide by whatever I added. I'm going to do the same thing here. I'm going to ignore the constant. It doesn't matter if it's a fraction. I'll add 1 to the top, and then I'll divide by whatever I added. And then I'll do the same thing here. I'll say I'll ignore the constant. I'll add 1 to the top, and then divide by whatever I added. So this simplifies to being 1 over 2 x to the 4th minus 2x cubed over 9 plus 5x squared over 2 plus c. And that would essentially be my answer. So let's go ahead and look at another problem here. So we have f of x equal to 4x to the -2/3. So actually, let me make it clear that this is an exponent, x to the -2/3. minus 2x to the 5/3. So the basic idea here is that we don't want to violate anything that we have been learning so far. So if we're taking the integral of this function, we ignore the constant, right? And then we're going to essentially do x to the -2/3 plus 1, right? And we're going to divide by whatever this was. So the question then is, what is -2/3 plus 1, right? What is this? But before I actually answer this question, I sort of want to digress for a moment. I mean, how do we easily add 1 without having to think too much into it? Suppose I asked you to do 1/2 plus 1. What would you say? Well, an easy way to do this is look at the denominator and just write 2/2, right? Or if you had 1/3, look at the denominator, and just write 3/3. Or if you had 1/4, just look at the denominator, just write 4/4. And because all of this is equivalent to adding 1. So 1/2, 2/2, this is 3/2, right? This is 4/3. This is 5/4. So if you want to add 1, if you had, like, let's say 5/4 and you wanted to add 1 to it, just look at the denominator and just say this is 4/4. And then this would be 9/4. You're essentially bridging that gap. And the same thing would work if you subtract. So if you have 1/2 minus 1, you just do -2/2, right? You look at the denominator and you essentially make it the numerator and the denominator. And then you bridge that gap, and then you just do the addition or subtraction here. 1 minus 2 is -1/2, right? If you had, let's say, 7/6, it doesn't matter, minus 1. Well, instead of saying -1, just say that it's 6/6, and then bridge that gap, and then say that it's 7 minus 6, which is 1/6, and that's your answer. So, this will really come in handy in terms of solving these types of problems where you have to sort of take 1 away and add 1, so on and so forth. And so what we would do in this case is we would say that, if we were doing -2/3 plus 1, instead of saying plus 1, we would just say plus 3/3, which is 1/3. And essentially this would be our answer, right? So we would say that this is this over here. We would say this over here. So if we were to do x to the -2/3 plus 3/3, right? And we're essentially dividing by whatever this is. So we know that this is, we know that it's 1/3, right? So we'll divide by 1/3 minus 2x. So we're going to ignore the constant. We're adding 1 to the top. So we're doing 5/3 plus 1. We're not actually going to do 5/3 plus 1. We'll do 5/3 plus 3/3, dividing by whatever this is. So 5/3 plus 3/3. So 5/3, I'm sorry, 5 plus 3 is 8. So that's 8/3, right? That's 8/3. So this actually comes about to being 4x to the, so this would be 1/3 over 1/3, and we would have 2x to the 8/3, right, over 8/3. Now, I'm essentially going to tell you a sort of a trick here, that if you have a over b over c, right, this is equal to CA. This would essentially be equal to CA over B. So essentially what has happened, so if you have like 2/3/4, this is, so you're essentially just flipping, you're multiplying this with this. That would just be 8, and then you're keeping this in the bottom. If that's hard to understand, let's say you had 2/3/4, right? This is the same thing as 2 times 4/3, right? Which is 8/3. So you're essentially just flipping this around. You're multiplying by the reciprocal of this. And if this is not too intuitive, leave a comment and I'll sort of write more into it. But that's sort of the basic idea. And so what we would do in this case is we would say that this is 4x to the 1/3, we're multiplying by the reciprocal of this, which is 3 over 1, which is just 3. Minus, and then again, we're doing 2x to the 8 over 3, right? But then we're multiplying by the reciprocal of this, which is 3 over 8. So we would have 4x to the 1/3 times 3 minus 6x to the 8 over 3 over 8. Okay, and let's see, this would come about to being, so we would have 4x to the 1/3 times 3, which would essentially be 12 if you think about it, right? We would have 12x to the 1/3 minus 2 can go into 6 3 times, 2 can go into 8 4 times, and so that this would essentially be our answer here. So let's actually go ahead and look at another type of problem. And so this problem is, let's see here. So this integral here would essentially be x squared minus 1 over x cubed dx. So the basic idea here is that you're looking at this, but you want to essentially split the fraction. So this is the same thing as x squared over x cubed minus 1 over x cubed dx. And the basic idea behind that is that if you have a plus or minus b over c, this is the same thing as a over c plus or minus b over c, right? Because there's a common denominator, so you can split them up in that fashion. And so that's essentially what we're doing here. So we've essentially said that, okay, taking the integral of this piece is the same thing as taking the integral of this piece here, where they're all sort of split up. And what we can then say here is that this is, we can sort of simplify the x's and whatnot. So we can say this is 1 over x minus 1 over x cubed, right, dx. And we know that, if we have two things being sort of added or subtracted together and we're taking the integral of that, then all we really have to do is take the integral of them individually. So we can take the integral of this individually, right? And we can take the integral of this individually. And that's really what we've been doing, right? We just haven't been sort of separating it in this fashion. And you can sort of think of it as, okay, let me just take the integral of this and the integral of this and combine them. Well, the integral of 1 over x dx is ln of x. So this is ln of x, right, minus, so I have to take the integral of 1 over x cubed dx, right? What's the integral of this piece here? Because remember, what I was doing back here was, and this is why it's helpful to actually show this stuff, I was splitting this up. I was taking the integral of this piece, which is, and then I was taking the integral of this piece, right? When it's complicated, it's very useful to split them up and sort of look at them. So the integral of 1 over x is ln of x. Why do I say this? Because what functions, remember what we were talking about before when we were introducing integrals. You're looking for a function whose derivative will give you back the original function. So here, you're looking for a function whose derivative will give you 1 over x. We know that ln of x gives us 1 over x, which means that ln of x is the antiderivative of 1 over x. So it's easy, it's useful to remember at least. This part here would just be ln of x, but we still have to do the integral of 1 over x cubed. So this is part of our answer. Ln of x is part of our answer. But then 1 over x cubed, what is that, right? So we can say that this is the same thing as x to the -3 dx. Why am I doing this? Because I want to be able to put the power rule. I don't know how to deal with 1 over x cubed, but I do know how to deal with x to the -3rd, right? Because if someone asked me to take the integral of x to the -3rd, then I can essentially just add 1 to the top and divide by whatever I had added. So in this case, I'll just say that this is ln of x minus, and then I'm going to add 1 to the top. So I'm going to say this is x to the -3 plus 1 over whatever I added. So -3 plus 1 is -2, right? So I'll just say that this is -2. So I have ln of x minus x to the -2 over -2. And that would essentially be my answer. And of course, you could simplify this to make it seem a little more, you know, aesthetic, as it were. So you would have ln of x, and you already have a minus here. This fraction is negative x to the -2 over 2, right? So this becomes positive. You have ln of x plus x to the -2 over 2. And then you can actually take this x down. But remember, when we take things down and we put them over the fraction, we actually have to change their sign. So this is ln of x plus 1 over 2x squared. We'll add our constant of integration, and we'll say that this is the antiderivative of our original function. So this is a very useful integral to look at because it demonstrates what we had in the last question as well. We have 1 plus under root t plus t over t dt. So in this case, it's not dx. We're not taking the integral with respect to x. We're taking the integral with respect to t. But a useful prerequisite here is that, you know, if we have the integral of under root t, you know, how exactly do we solve something like this? Well, the idea is that remember that, you know, if we were dealing with under root x, right? Under root x, we know that under root x is the same thing as x to the 1/2, right? Or if we have, you know, x to the 1/2, we know that's the same thing as under root x. So if I have under root t here, this is the same thing as taking the integral of x to the not x to the 1/2, but t to the 1/2 dt. And now I can just use the power rule that I'm really used to. I'll add 1 to the top and I'll divide by whatever I added. So I'll go ahead and say that this is t 1 over 2 plus 1, which I can say is just 2 over 2, divided by whatever this becomes, which is 3 over 2, right? I bridge that gap and I add these numbers. It's 3 over 2. So it's 3 over 2. So this is actually t 3 over 2 over 3 over 2. And then I take 2 3 over 2 and I multiply by the reciprocal of this. So that's just 2 over 3, which is 2t 3 over 2 over 3. And so that's how you would do this part, right? But as you can see, we have a much more complicated integral to look at. And so how exactly do we do something like that? Well, the idea is to essentially split it up in the same way that we've been splitting things up before. If they're essentially we can see that they all have a common denominator. So we're going to split them up, and we'll say that this is 1 over t, right, plus under root t over t plus let's see here, plus t over t dt. And then we'll sort of simplify to see if we can make our lives easier to take this integral. The first thing we notice is that, you know, we can't do anything with 1 over t. We can't cross these t's out, so we'll leave that as it is. And this t over t is just 1, so we'll say that this is dt here. And so now at this point, we can actually go through and take the integrals of each of them individually, right? We can sort of take the integral of 1 over t dx. We can take the integral of this dx. We can take the integral of just 1 dx. And then, you know, so what I'm trying to illustrate here is that if I have, you know, 3 things being added together or subtracted together, or even both, then I can sort of split my whole integral up into these little integrals where I can then just take the integral of them individually and then just combine them back together as they were originally. And I don't have to necessarily like write that down. I mean, you could do that in your head and say that, oh, I'm just going to take the integral of this, this, and this, and I'll just combine them together. This is sort of just an elaborate step to show you what's happening. And remember how we said that the integral of 1 over x is ln of x, right? And in the same way, the integral of 1 over t is ln of t. So this part would come about to being ln of t. So this part we will work on. I'll just leave it as that is right now. This should be a t. These all should be t's, by the way. And then so the integral of 1 is just t. So the idea behind that is if we're taking the integral of, like, let's say, 3 then, the answer to this is 3x. If we're taking the integral of 2x, or sorry, 2, then the answer to this is just 2x. So you can see a pattern that whatever variable we're taking the integral with respect to, in this case, we're taking the integral with respect to x. If we're taking the integral of a constant, we just add that variable. So if we're taking the integral of 3 dt with respect to t, it's just 3t. And it's not 3x anymore because the variable that we're taking the integral with respect to has changed. And so that's essentially the idea. So here, what we were doing was we were doing f of 1, right? F of 1 dt. So the integral of a constant is just, it's the constant, but it's multiplied by whatever variable we're taking the integral with respect to. So in this case, we're taking the integral with respect to t, so it's just t. And so that's why I'm saying, okay, well, 1t is just t, right? So I'll just leave t here. And so we have ln of t plus, and we haven't touched this middle guy here because we're sort of concerned about how to do this stuff, but then we have plus t here. So the question is, I mean, really we're done, right? But really the question is, how do we tackle that middle guy there? And the answer to that question is a little taxing to look at, but we'll look at it. So we'll sort of isolate this here, and we'll say, what is the integral of under root t over t dt? Now, the clear and cut rule is that, like, if you have a fraction, can you make that an exponent of some sort? Can you make it a polynomial so that it's sort of not a fraction, so that we can put the power rule on it? And think about it, right? I'm going to outline a chain of logic, and hopefully you can follow me here. So under root t, right, we know that this is t to the 1/2 over t to the first, right, dt. And what if I take this t up here? So I'll have t to the 1/2 multiplied by t to the -1 dt. And I'm going to actually combine the t's by, if you remember, the exponent rule is x to the a times x to the b is x to the a plus b. So if I have 2 to the 3 times 2 to the 4th, this is 2 to the 4 plus 3, right? So in this case here, I'm essentially going to say that this is the same thing as taking the integral of t to the 1/2 plus this -1. So plus -1 dt. So I'm just adding the exponents. I'm essentially just adding 1/2 plus -1, which is actually just 1/2 minus 1, which is actually just 1/2 minus 2/2, which is -1/2. So this is actually -1/2 dt. That's essentially what I'm working with here. And if I wanted to take the the integral of this, I would have to add 1 to the top and then divide by whatever I added. So this would essentially just be t. So the integral of this would be t to the -1/2 plus 2/2, adding 1 to the top, dividing by whatever I added. So this would be 1/2, right? Because if my exponent here is 1/2. If I bridge the gap and I add these, I'd get 1/2. So I would essentially have t, which is 1/2, and then I'm going to multiply by the reciprocal, which is 2/1, which is just 2. So I have 2t 1/2. So this middle portion here is actually 2t 1/2. So this is the same ln of t plus 2t 1/2 plus t plus c. Plus t plus c. And this is essentially my answer. You could put this in radical form. You could say that this is 2 under root t, but I mean, the answer still stands. So what if we had x to the -3rd dx? Or sorry, what if we had x to the 1 well, if we had the integral of x to the, or 1 over x cubed dx, how would we solve this? We would put it in a form that we can essentially apply the power rule of integrals. So we would say that this is the same thing as x to the negative third dx, and then we would add 1 to the top and divide by whatever we're adding. So we would do x to the negative 3 plus 1 divided by negative 3 plus 1, right? Whatever this is, we're essentially divided by. So negative 3 plus 1 is negative 2. So we would divide by negative 2. So this is x to the negative 2 over negative 2, which is 1 over negative 2x squared. So let's actually take a look at this problem here. So how do we solve this problem? Well, when you're looking at a combined fraction, the first sort of rule of thumb is to look if you can split it up, and we can split it up, right? We can say that you know, if we have a plus or minus b, right, over c, this is the same thing as a over c plus or minus b over c, right? Because they both have sort of a common denominator, so we can split them up. And so that's essentially what we're leveraging in this case. So so what we'll essentially do in this case is we'll say, okay, well, this taking the integral of this piece is the same thing as taking the integral of 3x over under root x minus 2 over under root x dx. And we know that if we're taking the integral of a sort of a function times another function, or sorry, a function minus or plus another function, then we can actually take the integrals of these functions separately and then come back and then combine them with whatever operation was bounding them together. And so that's essentially what we want to do, right? So we'll say that we'll take the integral of 3x under root x minus the integral of 2 over under root x dx. So we want to solve this individually, and we want to solve this individually, and then we'll just combine them at the end with subtraction. So essentially, how do we solve this piece here? Well, again, this isn't of the form where we can use the power rule. And so we want to essentially put it in a form where we can use the power rule of integrals. And so what comes to mind is that if you have this is the same thing as x to the 1/2, right? dx. And this, we can take it to the top, but we would essentially have to make it negative, right? So we would say x to the negative 1/2, right? I actually haven't taken the integral yet. I'm not using any integral rules. I'm essentially just re-expressing this function so that I can actually put myself in a better position to use the integral rules. And then minus, so I can minus this. Or actually, let me just go ahead and solve this piece first, and then we'll look at this piece. And so what strikes me in terms of simplification is how I can, how can I combine the x's? And the answer is yes. If I have x to the a times x to the b, then I can do x to the a plus b, right? I can just add the exponents. And so the exponent here is 1, the exponent here is negative 1/2. So if I do negative 1/2 plus 1, it's the same thing as doing negative 1/2 plus 2 over 2, which is 1 over 2. So I can essentially just do, this is a 1 here. I'll essentially just say that this is the same thing as taking the integral of 3x to the 1/2 dx, right? Which is fairly easy, right? I mean, I can just say that this is, so I'll ignore the constant. I'll add 1 to the top. I'll do 1 over 2 plus 2 over 2 over, so over whatever this exponent is. So 1 over 2 plus 2 over 2 is 3 over 2. So it's 3 over 2. And so that, and then of course I would just say 3x 3 over 2, and I want to multiply by the reciprocal. So I'm going to multiply by 2 over 3, which is 6x 3 over 2 over 3. And I'll maybe simplify this here. I'll say that this 3 can go into 6 twice. So I'll say that this is 2x 3 over 2. So I know my first piece, right? This is my first piece here, 2x 3 over 2. And then what about this piece, right? So right, so I can take this to the top, but before I do that, let me sort of outline the steps here. So I'll have 2x to the 1/2 dx, right? I'm not taking the integral again, I'm just sort of re-expressing it as if in another form. And then I'll take this guy to the top so that it's easier for me to take the integral. So I'll say 2x to the negative 1/2 dx. And then I can use the power rule on it. So I'll ignore the constant. I'll add 1 to the top, negative 1/2 plus 2/2, just ignoring the top here. And then adding 1 to the top, and then I'll divide by whatever this is. Now this would be what? It would be 1/2, right? So 1/2. So then I have 2x 1/2, right? And then I want to multiply by over 1/2. So I want to just multiply 2x to the 1/2 by the reciprocal of this, which is 2. So I have 4x 1/2. And remember that we were subtracting these, right? So your answer is 2x 3/2 minus 4x 1/2 plus c. So how would we take the integral of this? Well, we know that if we're looking at a polynomial, we can essentially break this down and take the integral of it individually, right? So we would take the integral of this, this, and this, and sort of do it individually. And so we can essentially do this by, so we'll go through and we'll ignore the constant here, add 1 to the top, divide by whatever we added. So we'll do 7x to the 3rd over 3 plus 5x to the square over 2 plus 10. So here, when we're taking the integral of 10 over x squared, like this is all fine, right? This stays in our answer, but taking the integral of this part here, so we'll have 7x cubed over 3 plus 5x squared over 2 plus, so taking the integral of this part is the confusing part. And the idea is that we want to put this in a form where we can sort of take the integral using the power rule and the constant rule. So we'll take this x squared to the top. We'll say that this is 10x to the negative 2, right? So we're taking the integral of this. And what this allows us to do is it allows us to have everything we had before, and then we can essentially just ignore the constant, add 1 to the top, and then we'll divide by whatever this is. This is -1, right? So our answer is 7x to the 3rd over 3 plus 5x squared over 2 plus 10 to the -1 over -1, which is 7x cubed over 3 plus 5x squared over 2 minus 1 over 10. Well, actually, sorry, it's 10x here. So forget what I said at the end. It's just 10x to the -1. So we can actually re-express this as 7x cubed over 3 plus 5x squared over 2 plus 10 over x, right? I'm just taking this to the bottom. And then this becomes negative because there is a negative here. So this is essentially our final answer. So we're looking at this here. How exactly do we take the anti-integral, the antiderivative? And the basic idea is that we want to just take the integrals of them individually, and then we'll sort of deal with it. So we're essentially taking the integral of this, right? And then we're taking the integral of this, and then we're taking the integral of this. You could do this in your head in the sense that you could split them up in your head, or you could write them down, ignoring the constant, add 1 to the top, divide by whatever we added. So add 1 to the top, divide by whatever we added, plus, so this is the same thing as, right? So actually this part, we'll just rewrite it as taking the integral of x to the 1/2, and then we'll get back to that in a second. So here we ignore the constant, we'll add x to the -3rd. So we would add 1 to the top, -3 plus 1, right? Which is -2. So this would be -2, and we'll divide by -2. And so this is part of our answer, right? This is set. And then this part here, so we'll ignore the constant, we'll add 1 to the top, we'll do 1/2 plus 2/2, right? And that's 3/2. So we'll divide by 3/2. plus we already, so this is negative, right? 2x to the negative 2, right? This cancels, becomes 2. And so our answer is 8x cubed over 3 plus 4x to the 3 over 2 over 2, or sorry, over 3 minus 1 over 2x squared. So what did I do, right? I multiplied this by the reciprocal. So if you flip this around, you would get 4 over 3. And then here I had 2. Oh, oops, I should not do that. I had 2 here, and then I brought the x squared to the bottom. So I actually had to switch the sign around. And then I added my constant of integration, and this is what I have. So I actually want to now transition. We were looking at integrals, and now we want to essentially transition to looking at questions that want you to essentially find the original function by looking at the something called initial conditions. So it could, a question could say, find f if so the basic idea, right, sort of like a prerequisite here. The understanding is that if you have a function, right, and you have the derivative, and you have the second derivative, the basic idea is if you take the integral of the derivative, then you will get the function back. If you take the integral of f prime prime, then you will get the first derivative back. So the order is like this, right? So if you take the integral of this, you will get this. If you take the integral of this, you will get this. And so that's essentially how it works. So if I take the integral of f prime prime, then I would essentially get f prime. If I take the integral of f prime, I would essentially get f. And so that's essentially how that would work. It's telling me to find f, and they're giving me f prime. So if I take the integral of f prime of x, I will get f. So noting that, just noting this factor, this concept, if I take the integral of 3x, then I will get the original function back, right? And so if I do that here, I would essentially have, I would essentially have, I would ignore the constant, and then I'll add 1 to the top, divide by whatever I added, plus c, right? So this is my original function. Now it's not, so this is the function, right? But it's a general solution. Like this is the general solution. Because it has the c in it. It's not exactly the solution, it's the general solution. So it's like it contains many functions. C could be anything. So now we actually have to solve for c. So how do we essentially do that? That's essentially the question, because this function that we're talking about, it represents many functions, and so we can't really say that, if the question was asking for like a general solution, then we could say that this is the answer. But if it's asking for a more specific function, then we would actually want to solve for c and figure out what c actually is, and then we would get to a solid conclusion. So how we do that is we plug in this number into the function, right? So we do f of 0, and we get 3 times 0 squared over 2 plus c. F of 0 equals 0 over 2 plus c. f of 0 equals 0 plus c. So that means f of 0 equals c. And we know that f of 0 is 7. So we replace this with 7. And then we get that 7 equals c. So we can then go back here and we can say that, this was our general solution, but our specific solution, f of x equals 3x squared over 2 plus 7. This is the more specific function. So what did we do? Where were we? We had this f of x equals 3x squared over 2 plus c is what we had. And what we did in essence was we know that if we plug 0 into the function, we get 7. So we plug 0, we do f of 0, and we see that this goes to 0, right? So this means f of 0 equals c. So we're just solving for everything that we know. And we know that f of 0 is 7. So that means we can put 7 here, and then we will get c. So 7 equals c. And so we can now go back to our general solution and then substitute 7 in, and that would essentially be our answer. And we can cover more examples. So this question in particular, again, it's asking us to find the original function. We know that if we take the integral of f prime, then we essentially get back the original function, but it's the general solution. And so we want to both find the general solution and then we'll solve for c given the initial conditions. These are the initial conditions. So again, right, if we take the antiderivative of the derivative, then we will get the original function. So we're actually given the derivative, right? It's 6x squared minus 5 dx. So if we sort of solve this, we ignore the constant, and then we'll add 1 to the top, divide by the top. So we'll add 1 to the top and divide by that exponent that we have up there. And then we'll do this here plus c, which means that f of x is equal to 6x cubed over 3 minus 5x plus c. And the idea here is that, now we want to sort of solve for this c guy here. F of 1 is equal to 4. So if we plug in f of 1, right? So we've plugged in 1. And if we solve, f of 1 equals 6 over 3 minus 5 plus c. F of 1 is equal to 2 minus 5 plus c. F of 1 is equal to negative 3 plus c. We want to solve for c, but there's a missing component. The missing component is f of 1, which we actually have here as being 4. So we'll say 4 equals negative 3 plus c. Now we can actually solve for c. We can say this is 4 plus 3 equals c, which is 7 equals c, which means now we know what c is. We can go back to our general function, and we can put the c as 7. So we'll say that f of x equals 6x cubed over 3 minus 5x plus 7. And of course, we can simplify this to say that this is 2x cubed minus 5x plus 7. And this is our f of x, a specific solution. So this question, what we were given before was we were given like the first derivative, but now we're given the second derivative. We want to find f. It's going to take us longer to get there. You want to note that if you have f prime, and if you take the integral of f prime, then we get the original function, a general solution. But then if we have, f prime prime, then we get f prime. So if we put f prime into the integral thing, then we get f prime out. And then once we get f prime, we can map ourselves back here, and then we'll map ourselves back here to get the original function. So if I put the f prime prime into the integral, then I get f prime. And then once I have f prime, I can put that into another integral and then get the original function back. The only difference is that I may have to do a little more work to get the exact specific f prime. So what do I mean? So let me put the second derivative into the integral, and that will give me the first derivative, but it will give me a general solution. Then I will get a specific solution from the first derivative. So if I put the second derivative into the integral to get the first derivative, I'll actually be putting 2x minus 3, right? Because that's the second derivative. And then once I do this, I'm going to take the integral of this, and then I'm going to merge them together. So I'll ignore the constant 2x squared over 2. So minus 3x plus c. So this means that this is my f prime, right? This is my f prime of x is this guy. And you can see that this is a general solution. It's not a specific solution. So in order to make it specific, I would essentially have to find out what c is. Let me go ahead and cancel these out. So what I will do is it tells me that if I put 1 into f prime, I will get 2. So let me go ahead and try putting 1 here. So I'll get 1 squared minus 3 times 1 plus c, which is 1 minus 3 plus c, which is negative 2 plus c. F prime of 1, they're saying is 2, right? So I can put 2 here, and then I will get 4 equals c if I add this to the other side. So 4 is equal to c, which means this is my general solution, right? But then my specific solution would be f prime of x equals x squared minus 3 x plus 4, because I know that now my c is 4. So this is f prime, right? And now if I want the original function, I just have to take the derivative and put it into the original function, and I will get the original function back. So if I want to do this, I would have to put this inside here. So that would look something like so. Now that I have this, I can take the integral of this, and that would give me the original function. So I will have x cubed over 3 minus 3x squared over 2 plus 4x. So this is f of x, right? But plus c, right? It's a general solution. It's a general solution if you don't plug it in. Whenever you're taking the integral, it's a general solution. But they give me a clue that f of 0 is 3. So I'll take f of 0, I'll take 0, I'll plug it into the function. So this goes to 0, this goes to 0, this goes to 0. So it says f of 0 is equal to c. Now f of 0 is what? F of 0 is 3, right? So which means c is equal to 3. So that means that this is my general solution. My specific solution would be x cubed over 3 minus 3x squared over 2 plus 4x plus 3. I just put that c here. So what did we do? We had f prime prime of x, right? This is what we had. And then we said, okay, if I put f prime prime of x into the integral function, then I'm going to get f prime plus c. And then we solved for the c. So we got f prime, we actually got a concrete value for f prime. And so then we took the f prime, we put it into the integral function. And then we got f plus c, and then we solved for c, and then we got f. Let's look at another example. It says to find f if f prime of x is 8x cubed plus 1 over x, f of 1 equals -3. So the idea behind this is to understand that if I take the integral of f prime of x, then I will get f, a general solution. So this would essentially, so I will take this and I will put it into the integral function. I will get 8x cubed plus 1 over x dx. This is the same thing as taking the integral separately. And I'm going to ignore the constant, add 1 to the top, divide by whatever I added. So 8x to the 4th over 4 plus the integral of 1 over x is ln of x plus c. So this means that my f of x equals this. This is the general solution. I want a specific solution, which is why I'm looking here. So I'll essentially substitute 1 into the function. So I'll say 8, 1 to the 4th over 4 plus ln of 1 plus c. I'm solving for c here. F of 1 equals 8 over 4, which is 2, plus ln of 1 is 0, plus c. So now f of 1 is -3, so -3 equals 2 plus c, -3 plus 2 equals c, -1 equals c. Well, actually, sort of taking a step back here, once I take 2 to this side, it should actually be -2 equals c, so -5 would equal c. And so I have my general function, but now I'm just going to replace this guy to be -5, and then this would be my this would essentially be my function here. So this one is saying to find f, and f prime prime of x is equal to e to the x minus 2 sine of x. And it's saying that if you plug in 0 into the function, you'll get 3. And if you plug in pi over 2, you'll get 0. So just, just note that if you plug in, if you take the derivative of, if you take the integral of the second derivative, then you get back the first derivative, right? And then if you take the first derivative, then you will get back the original function. These are both general solutions. So essentially what you would do is you would first take this guy and put it into the integral to get f prime, and then from there you would get f. So if I were to put it into the integral function, I would have e to the x minus 2 sine x dx. So this would essentially be e to the x minus 2. So if you're taking the integral of sine of x, you're looking for a function whose derivative you can take such that you get sine of x back. And the answer to that would be negative cosine of x, I believe, because if you take the derivative here, so the derivative of cosine, well, yeah, the derivative of cosine is negative sine. So you'd have negative sine of x, which would be sine of x. So this means that this should be, since we know that the integral of sine of x is negative cosine of x, this should essentially be -2 plus c. So that means f prime of x is equal to e to the x plus 2 cosine of x plus c. This is essentially the general solution. So it's not exactly the exact solution. And so we actually want to solve for c, and we would essentially, well, we actually can't solve for c for f prime because it actually hasn't given us a hint as to what we should plug into f prime to get the value of c. So we're just going to take the integral again of f prime. And then once we do that, we would essentially be taking the integral of e to the x plus 2 cosine of x plus c. Remember, c is a constant, and that if you're taking the integral of a constant, like let's say 3, it's just 3x, right? So if you're taking the integral of c, it would just be cx. So in this particular case, you would essentially just have e to the x plus 2 sine of x plus cx. Remember, you have to add that x, right? And then that constant of integration, since we've already used c, we'll just use d instead. So we'll say that f of x is equal to e to the x plus 2 sine of x plus cx plus d. And that would essentially be our function, right? But we actually want to use this information now to solve for these two variables, c and d. So we'll essentially plug z. So we were given two pieces of information. The first was that f of 0 is equal to 3, and that f of pi over 2 is equal to 0. So what we will do as a result is we will say, okay, well, what's f of 0? We would do e to the 0 plus 2 sine of 0 plus c of 0 plus d. And that essentially kind of gets rid of the c value here, as it were. So f of 0 is equal to 1 plus 2 sine of 0. Sine of 0 is 0, so 2 sine of 0 is 0. So it's just 1 plus 0, which is 1 plus 0 again, because c times 0 is 0. So it's 1 plus d in a way. F of 0 we know is 3. So that's 3 equals 1 plus d, which is 4 equals d. Or actually, I would have to subtract this here. So this would be 3 minus 1, which is 2 equals d. So technically, this is my this here is my general solution. So f of x equals e to the x. So I've only solved for d, which means I can only substitute d back here. So e to the x plus 2 sine of x plus c x plus d, which is 2. And now that I have d, now I'll just substitute for c. So I'll say that I'll take this other guy here, pi of 2. So pi of 2 equals e to the pi of 2 plus 2 sine pi over 2 plus c plus 2. And f of pi over 2 we know is 0, right? So we'll say that this is e to the pi over 2 plus 2 of sine. So sine of pi over 2, this is pi over 2. The y value at pi over 2 is 1. So this is just 2 times 1, which is just 2, plus c times pi over 2. Can't do much with that. This, I guess, just has to be pi c over 2 plus 2. 0. So we'll try solving for c here. That's our goal. So sorry, this is our goal, to try to solve for c. So I guess instead of putting it like this, I'll just make it a little more obvious that I want to isolate the c. So I'll put the c here. And what I'll do is I'll combine these. I'll say that this is 0, 4 plus c, or this is e pi over 2 plus c pi over 2 plus, yeah, I already added the 2's. So I'll take this to the other side. I want to isolate the c basically. I'll take this to the other side. I'll say that this is -4 minus e to the pi over 2 equals c pi over 2. And then maybe I'll divide both sides by pi over 2. So I have -4 negative e pi over 2 over pi over 2 equals c. And again, I'm going to take this and multiply by the reciprocal. So that means c is equal to -2 for negative e pi over 2 over pi equals c, which essentially means that this is my function. So I'm just going to put this, I'm going to put this where c is, and that would be my answer. So now I actually want to look at something called U-substitution. And the basic idea behind this is that we treat this as an actual arithmetic it's basically something we can actually do algebra with. And I know that sounds kind of weird and counterintuitive, but it's a differential, sorry, it's a, I don't want to get into that, but we just know that it's not just notation. We can actually perform, you know, arithmetic manipulation, arithmetic-based manipulation, or algebra-based manipulation on it. And so, you know, these integrals are a little more hard to do, but we essentially, what we do is so there's this technique called U-substitution, and we would essentially let u equal this this complicated part here, which is x squared plus 5. So we let u equal x squared plus 5, and the basic idea here is that we take the derivative of u. So remember that, you know, if we have x, for instance, then d over dx of x, well, you know, what we could also say that this is, you know, if we're considering t, for instance, then d over t over dx, right? That this notation would be very similar to saying that we're taking the derivative of t. D over t would just be 1, right? So the same idea here with U-substitution, you know, du over dx, the derivative of u with respect to x would be 2x, right? And then we actually want to start treating this as an equation. There are many ways to sort of do this. I usually multiply both sides by dx. The dx's cancel out. So I have du equals 2x times dx. And then I can isolate dx. Or actually, I could isolate dx by dividing by 2x. So I'll have du over 2x, which is equal to dx. So dx I know is equal to du over 2x. So I can actually replace this dx. So I'm actually replacing two components. The first component I'm replacing is this guy. I'm making this a u. And then this guy, I'm making this everything that I have here, du over 2x. So the idea behind that one is that I can say that this is now, so I made this, I made it a u cubed, and then du over 2x. That's what I said, dx is equal. So I've replaced this with du over 2x, and I've let the inside become u. And so now I can sort of simplify this a little bit. I can say this is 4x u cubed over 2x du. You want to think of these components as being multiplied, and this cancels out with this entirely. I leave behind a 2, so I have u cubed du. And I can actually pull the constant out, so I can say that this is 2 times the integral of u cubed du. And so at this point, I can say this is just 2, and then I'm just doing the integral of u cubed, which is 2 times u, I ignore the constant, 2 times u to the 4th over 4 plus c. And then at the so I'll simplify this a little bit. I'll say this is u to the 4th over 2 plus c. And then at the very end, I'll just put my u back, which was x squared plus 5. So this is x squared plus 5 over 2 plus c. So for this question, it seems like we're doing x cubed over 2 plus 4, or x to the 4th squared dx. And so we'll essentially let u equal 2 plus x to the 4th the inside stuff. And so that's one idea. The other is to say, we're going to take the derivative of u. So we'll take du over dx. What does that equal to? It equals to 2 plus, well, not 2, the 2 goes to 0. We have 4x to the 3rd. And then we'll actually solve for, I solve for dx. I mean, people do it differently, but du equals 4x cubed times dx. And I'll divide both sides by 4x cubed. So I have du over 4x cubed equals dx. And then, so now I can essentially omit this dx from here and replace it with this guy. So I would have, so I had x cubed, right, over 2 plus over u, because remember I let u equal 2x plus 4, 2 plus x to the 4th squared. And then the dx I've essentially replaced. The dx has been replaced with du over 4x cubed, right? So du over 4x cubed. And remember, this is multiplication, right? So this is the same thing as x cubed over u squared times 4x cubed du. These x cubes cancel out. So I have 1 over u squared times 1 over 4u squared du. I can pull the 1/4 out, and I'll have 1 over u squared du. And I can say that this is, so to put it in a form that resembles power rule, I can say this is u to the -2 du, which is 1 over 4. And then I'll do the power rule. I'll do u -2 plus 1 over whatever I have. Well, I actually won't use the integral sign here, but I'll say 1 over 4 times u to the -2 plus 1 over -2 plus 1. -2 plus 1 is -1, so that's it's consistent. So then I have u to the -1 over -4, which is 1 over -4u. I took this down. And now I can just simply put the u back. The u was 2 plus x to the 4th. Plus c, of course. Let's take a look at this one. It says find x cubed cosine of x to the 4th plus 2 dx. Basic idea is to let u equal x to the 4th plus 2. Take the derivative du over dx equals 4x to the 3rd. And then, of course, solve for dx. isolate the dx basically is what I'm trying to do here. So I now know that dx equals du over 4x cubed. And so what I can do here is I can say that this is x cubed cosine. I let the x to the 4 plus 2 be u. So that is x to the 4 plus 2. And then the dx is replaced by du over 4x cubed. So, and at this point, it would just be a matter of re-expressing this as x cubed cosine x to the 4th plus, well, so the inside here, I've actually restated as being u. So, and at this point, I can just say that this is x cubed cosine of u cosine of u, and then du over 4x cubed, and the x cubes cancel out, so I have cosine u du over 4, and I can actually say that this is 1 over 4, just the cosine of u du, which is equal to 1 over 4 sine of u, which is the sine of u over 4 plus c, and the u in question was x to the 4th plus 2, so this is sine of x to the 4th plus 2 over 4 plus c. This is another question for U-substitution, 2x under root 1 plus x squared dx. So we'll let u be equal to 1 plus x squared. Du over dx will be 2x, and then we'll solve for dx. So du equals 2x times dx. Dx will equal du over 2x. So two substitutions, well, not two substitutions, but u will be this portion here, and I'll replace this portion here. So I'll say this is 2x times under root u, and then the dx was replaced by du over 2x, so du over 2x, which is the same thing as 2x times under root u du over 2x, which is under root u du, which is u1/2 du, which is u1/2 plus 2 over 2 over 1 over 2 plus 2 over 2 is 3 over 2, so 3 over 2, which is u3 over 2 over 3 over 2, which is 2u 3 over 2 over 3, because I multiplied by the reciprocal. And then, you know, the u I would replace, right? So I would say my u was 1 plus x squared. So I'll say that this is 1 plus x squared, 3 over 2 over 3 plus c. So another question here, 2x plus 1 dx. Let u equal 2x plus 1. And then we'll take the derivative d over dx equals 2. And we'll solve for dx. So du equals 2 dx. Dx will equal du over 2. So we let u equal this portion here. We let dx equal this portion here. So this becomes u under root u, and then du over 2, which is under root u over 2 du, which is 1 over 2 f, or not f, but integral u1/2 du, which is 1 over 2 times u1 over 2 plus 2 over 2 over 3 over 2, right? Because this becomes 3 over 2. So this is 1 over 2 times u 3 over 2 multiplied by the reciprocal, which is 2 over 3. These cancel out. I have u 3 over 2. And then my u in question was 2x plus 1. So this is 2x plus 1, 3 over 2. I actually also had a 3 here, so I'll just add that 3 and a plus c. So this is 5x dx. So we'll let e to the 5x, well, not e to the 5x, but we will let u equal 5x. And we'll take the derivative, du over dx equals 5. And du will equal 5 times dx if we take this to the other side by multiplying both sides by dx. And then dx will equal du over 5. So this becomes e to the u. And then dx we said was du over 5, so that's du over 5, which is e to the u over 5 du, which is 1 over 5 integral e to the u du. Integral of e to the u is just e to the u, right? So it's just e to the u over 5, which if I put my u back, it's 5x. So it's e to the 5x over 5 plus c. So I have 2x cosine x squared plus 1 dx. Let u equal x squared plus 1. And here I'll essentially say that du equals 2x times dx. Dx equals du over 2x. So I'll say that this is 2x cosine of u du over 2x, which is 2x cosine of u du over 2x. These cancel out. Cosine of u du, which is just sine of u, which if I put my u back, it's x squared plus 1, sine of x squared plus 1. So if I have x squared under root x cubed plus 1 dx, I will let u equal x cubed plus 1. And essentially what I will say here is that du equals 3x squared times dx, and dx would essentially equal du over 3x squared. So now I can substitute for dx, and I can substitute for this as well. So I'll say that this is x squared times under root u times du over 3x squared, which is the same thing as x squared times under root u du over 3x squared. These would cancel out, and I would have under root, I'm sorry, not under root, but integral u to the 1/2 over 3 du, which is 1 over 3 integral u to the 1/2 du, which is 1 over 3 u, 1 over 2 plus 2 over 2 over 3, which is 1, which is u 3 over 2 over 9, because you multiply these. And then you have, so your u value was x cubed plus 1, so this is x cubed plus 1 over 9, 3 over 2. But I think I forgot something here. That this was actually, yeah, so let me go ahead and back up here a little bit. So we were doing 1 over 3, and then u 1 over 2 plus 2 over 2, which is 3 over 2. So this is 3 over 2 like this. And then you have 1 over 3 times u, 3 over 2, multiplied by the reciprocal, which is 2 over 3. And so you actually have 2u 3 over 2 over 9 plus c. And your u value is x cubed plus 1. So you have 2x cubed plus 1, 3 over 2 over 9 plus c. So this is the integral for x under root 1 minus x squared dx. Let u equal 1 minus x squared. Du over dx equals 1 minus x, would equal the derivative of that, which is 0 minus 2x. So just minus 2x. So du equals minus 2x times dx, which, so dx equals du over negative 2x. So we can say that this is x u du over negative 2x. This cancels out. So I have under root u over 2 du, which is 1 over 2 under root u du, which is 1 over 2 u 1 over 2 du, which is 1 over 2 u 1 over 2 plus 2 over 2 over 3 over 2, which is 1 over 2 times u 3 over 2 multiplied by 2 over 3, which is u 3 over 2 over 3 plus c, and my u value was 1 minus x squared, so 1 minus x squared over 3 over 2 over 3 plus c. But negative, because I was supposed to carry this negative, right? This negative here is supposed to carry through. So what about this one here? You have 4x under root 16 minus x squared dx. Let u equal 16 minus x squared. And then du equals, wait, I think we just did this question, didn't we? Something like it, whatever, it's okay. So du equals 0 minus 2x, right? So times dx. So du equals negative 2x times dx. Dx equals du over negative 2x. So we can substitute this part with this. So we can say that this is 4x under root u times du over negative 2x. This is 2x negative 2 u du, which is negative 2 u. 1 over 2 plus 2 over 2 is 3 over 2. 3 over 2, so that's 2 over 3, which is negative 4 u 3 over 2 over 3 plus c. And that would essentially be, so what we would have here is we would take this and it would be negative 4, 16 minus x squared, so 16 minus x squared. 16 minus x squared, 2 over 3